to Steve. A little bit about Steve. He's the managing partner of Star Fox Helium, owner of Running Foxes Petroleum, and president of Atoka Geochemical. He's got 40 years of experience in oil and gas, water flood, coal bed methane, renewables, nuclear, and mining. He's a very busy guy. He's got a PhD from School of Mines here in town, a master's from Southern Illinois University, and a BS from Northeastern University in Boston. Dr. Tedesco has written several articles on surface geochemistry, operations related to coal bed methane, gas production, Pennsylvanian geology of the Cherokee, Forest City, and Southern Denver Basin. And he's actually got a textbook coming out on surface geochemistry and petroleum exploration to be published later on this year, titled Helium, Carbon Dioxide, and Nitrogen Deposits. So that's pretty exciting. Dr. Tedesco has also found several oil and gas deposits, such as the Arickaree Creek field here in Lincoln, Colorado, and then found new reserves in several fields in the mid-continent and developed a number of water floods, such as Devon Field in Kansas and Thompson Field in Missouri, to name a few. So, Steve, we're really happy to have you here. Take it away.
Correct something, I've already published the Surface Geochem Petroleum book. That was back in '95, and I'm publishing with Elsevier a helium book. I'm sorry if I miswrote that. So that was my fault. Anyway, so what I'm going to discuss today, and thank you all for coming, is helium. It's gotten very pricey in a lot of respects because of changes in our modern society. And as such, it's become a very needed commodity if you want a modern society with healthcare, modern healthcare, computers, and welding and all sorts of other things. And the question is, when I got into it probably 3 or 4 years ago, really started looking at it, does it make sense for oil and gas operators to get into it, or is it very niche business, or is it more a business model for companies that like ExxonMobil, the national oil companies of Algeria and Qatar and Iran, or can the small operators really make money doing it? And that's the real question. So let's start with what is helium. I noticed the list of people. I know a lot of you know something about helium. I've learned more than I ever want to know right now. But a helium is basically an inert element. It doesn't combine with anything unless you have some severe high pressures or temperatures in which you can make compounds, but that is sort of extreme. And you don't see those on Earth or in any other planets. You might see them in the sun, but it's even doubtful there. There are 2 helium isotopes that are very important, and their importance is quite different, but it's leading the search for helium. Helium-3 is only formed in the sun, but it's critical in fusion. As a matter of fact, if fusion is to work without any byproducts of waste and that sort of thing and radioactivity, helium-3 will be critical in fusion reactors. And I'll get into where we find that a little bit later. Helium-4 is what we normally use in the all sorts of industries. It is basically 99.9% of the helium we find, and it's what we're really chasing. Helium is far more abundant. Oh, I just said that. Helium is less than, it's about 5 parts per million in the Earth's atmosphere, pretty constant, 5.2 to 5.6 ppm. It's got the lowest boiling point, which makes it easy in terms of getting separated from everything else, except that you have to get the cryogenic units down to that temperature for it to drop out. The only impurity really seems to be neon, which is also another element that's in high demand. Instead of $300 an MCF, as we see with helium, it's in the $5,000 to $13,000 range for an MCF in neon. But before you race out to look for neon deposits, so far there are none, and it's taken out of the atmosphere. Well, the origin of helium in the Earth, most of the helium-3 that we think is in the planet was trapped there by when the planet was forming. It got its helium from the sun. The sun generates helium-3 all day long and very little helium-4. Helium-4 is generated by decay of uranium and thorium um, elements. The only problem with that is it takes a billion years plus to generate one atom. Subsequently, it takes quite a while to generate a lot of helium. And so theoretically, the helium reserves we receive today that we're producing or capturing is basically from billions of years ago that it was generated. Lithium also generates helium. The extent that it does is, based on what I've read, is really not clear. Theoretically, they've done a lot of work on helium being generated from the Earth. Basically, a helium molecule will be generated and eventually finds its way into space. That's supposedly the migration tendency. So what do we use helium for? Cryogenics is the primary use. It creates an inert atmosphere for growing silicon and germanium crystals. So computer chips is another primary use. And because if we didn't have helium, a lot of our advances in terms of speed with computers and memory would not be there. Manufacturing our fiber optics, pressurizing and purging, cooling medium for nuclear reactors. Now, in some cases, you might think this is 100% helium, but if a gas has 10% helium, it actually has a lot of the characteristics needed that helium brings to the table to work. So it's not exactly a pure helium gas that people are using. Welding, leak detection, synthetic breathing mixtures, lifting, blimps. Actually, there's been a proposal out there to use helium blimps with internet systems attached to them and float them over in rural areas. This came from Silicon Valley as a way to get rural areas internet capability. I don't think they looked at the cost of the helium or the weather problems that would be related. Then fusion, the first fusion plants in southern France, but it's going to require boatloads of helium. And the only people who make helium-3 right now, other than trying to capture it in a variety of ways, is the US and the Russian military. So you can see where that's going. The other thing is, you may have noticed the Chinese are starting to put or attempting to put a base on the moon. The reason is the moon is covered with helium-3. As a matter of fact, there's been a lot of talk the past 5 years about space race in terms of mining helium-3. There's a recent movie out that the basis was the mining of a helium-3. I forget the name of the movie, but it was rather fun to watch. But helium-3 is in large amounts. It would supply the Earth with material for fusion forever. It'd be unlimited because basically the helium-3 crashes on the moon as well as on Earth, but it's accumulated on the moon. So it's certainly something to think about, but not pertinent to this talk. And here's just a diagram showing the uses of helium. MRI units use it all the time. Without them, we can't image ourselves and hopefully get better medical care. Okay, so no helium, then no MRIs, no helium, then you can see the type of computers we'll use in the future. So helium is very critical. The question is that, is it economic to look for, and how do you find it? In terms of reserves and production, this is a diagram showing how helium supplies are increasing. The consumption's increasing, but the supplies are decreasing. The Texas Panhandle and Hugoton fields, which is one of the original fields that started producing it, is in decline. The BLM has shut down its processing facility. And basically there are a number of helium processing facilities that are private around there that are desperately looking for helium. And there may be ways to find more helium in there, but essentially the field is at the end of its life. Russia and Qatar have very large reserves of helium supposedly, and there's a concern that it will depress the price. I have several European partners, and some of them work with people who work in Qatar. And right now the helium production there, believe it or not, is shut down, and I can't tell you why. The deposit, which I'll show you, that Qatar produces out of, Iran owns half of, and Iran says they're not producing any, but then they have their nuclear program, which they're restarting, which they'll need helium to do that. So we can conclude, if you want, that maybe Iran is not telling the truth. The Russian facility called Amur is not a field. It is basically a processing plant tied to several pipelines with pretty much low percentage helium, but enough with the large amounts of gas to process. The problem with data from the Russians, as sometimes with a lot of people, is that they send out misleading data or it's not quite correct. Regardless, I don't think that helium is going to be in oversupply anytime soon. A lot of the helium that's coming online is in areas where it's politically unstable. The economics, well, 20 years ago, there wasn't really very good economics. The BLM controlled pricing, and Congress would occasionally change things, and then that would drive out private operators from the helium industry. Right now, we're at $300 an MCF. It may have fallen to $250 because of the pandemic, but it's pretty much stabilized. New sources of helium coming on. Well, there's still plenty of expansion in the healthcare industry as well as fusion. The military uses 25% of the helium produced in the US, like they use 25% of the oil and gas. Subsequently, they're expanding their use of high-tech equipment, which requires helium. So the economics right now look very good. And typically, a processing cost is about $150 an M for an MCF of helium. So where's helium from? Mantle, crustal, solar wind, and I half-kiddingly say magic because sometimes I can't figure out where the helium's coming from. A lot of it is theoretical and conjecture. We do know uranium, thorium, lithium, carbonaceous mudstones, which have uranium and thorium in them from decay. The reality is in the Texas Panhandle, there's been a number of studies trying to figure out how we got so much helium, even though it's a very low percentage relative to the amount of gases there, how we got that helium there and where did it come from. And I know I talked to a couple people and saw a couple papers if they take all the helium that was the Hugoton, they can barely get that amount of helium out of the Anadarko Basin. So there's more helium out there than I think people can recognize, and there's probably more areas where helium is coming up from. And I think it's very difficult to find the source of this helium because the basement tectonics and history, it's very hard to define those based on the data that we collect in the oil and gas industry. Many people don't drill wells to basement and analyze the granitic rocks. Obviously, there's reasons why for that. So the source of helium is still up for conjecture in a lot of ways. As I said, 5.2 to 5.6 parts per million in the atmosphere, and it's constant. And that's a number that's relatively constant to me. That means we're ejecting helium as fast as it's going into the atmosphere. As I said before, helium takes years, billions of years to generate, and there are some problems with helium supply and estimation. So how does helium migrate? Tyler Weissman and his partner McBride did a course shortly, and they presented several sort of models, but basically this is the simplest model. You do need structure, in my opinion, for every helium deposit, and just about every field that I've looked at, including Morrow fields, has some sort of structure in the Morrow sand, and you see the high helium numbers there. But essentially you get leakage from the basement or crustal rocks or the mantle that migrate up into a reservoir, and the seal being good enough gets to migrate to the top of a structure. It's a very simple, it'd be hard to figure out where the helium's coming from. The concentration in the migration paths actually might be from several different sources and not one specific intrusion. So we have remobilization of HE in the crustal sediments. As I mentioned, the Anadarko Basin. The map on the left is from my PhD. It's derived from I think that I saw it on a bookcase in previous, from Mr. Kubik's slide. And it basically, it all gets generated and moved out. And that's why we see where the central Kansas Russell Rib, we see a lot of helium up against Precambrian ridges trapped in Simpson sand or shallow Permian reservoirs. Same with the Texas Panhandle. All of that is the end point where migration out of the Anadarko Basin. Basically, all the plumbing just ended. It's like a capped well. There are three types of deposits: HE with methane, HE with nitrogen, and HE with CO2. They all have different characteristics. In all honesty, I don't think HE has too much of a relationship with anything. It's just the combination of the other gases that were present when the HE was accumulated. Preferably, We like nitrogen because you can vet the nitrogen to the atmosphere during processing. The problem with that is if it's all nitrogen like at Harley Dome, you don't have any natural gas to generate electricity from, which means your costs go up. Then if you have methane, the problem is you have to have something to take away the methane, such as a pipeline, or you could be stranded by having too much methane or other hydrocarbons. And then if it's CO2, same thing as the others. If you can put it into secondary recovery fields next door, great. If not, you got to figure out how you're going to vent CO2 in the present political climate. The size of deposits vary, and I've given some examples. Low-grade deposits are actually the real important ones, because basically they provide 90+% of all the helium in the world. And they're the ones that where you could have 0.04% helium and make money at it. For example, Qatar, the North and South Pars field that Qatar and Iran share has that low level percent helium, but it has 1,800 TCF of gas. So that means it has a significant amount of helium. So you can strip out all sorts of things at low percentage from high reserve type of deposit of that. Moderate grades, Otis Albert, Battle Creek, which is up in Saskatchewan, which has come online, being developed by North American Helium. And then real low grades. These typically are like in mining. They're the high grade vein deposits like Central City, whereas porphyry coppers are like the low grade deposits. The problem with the high grade deposits is they are, a lot of them are real teasers. A lot of areas in the country where you see them, but many of them don't pan out. You get very high numbers, but there's no reserves. There's no sort of continuity and lateral extent to them. They look great, but unfortunately, they just don't turn out to be economic. So what is a Pathfinder tool for helium? Well, really nothing. We do a lot of work showing helium's relationship to nitrogen. Well, in reality, the two don't have an association because they can't combine. So why are they together? Well, they could be being vented together, or the nitrogen is coming from clay minerals and released, and the helium's present. So we see variations in helium and nitrogen in various deposits that look different. The CO2 is typically, in most cases, especially the high CO2 deposits like Labarge. There's some in Utah, Woodside, I believe. That's from venting from the volcanic activity, igneous activity below. And helium's just coming along for a ride. So in many respects, looking at the nitrogen, CO2, and all that sort of ratios, to date, I haven't found them as a great Pathfinder tool. Basically, the best Pathfinder tool is going around and testing everybody's wells to see if you can find something. And as I said, the massive nitrogen fields in Germany have no helium in relationship to them. So we do know that the source for helium, being from the crustal or mantle, sometimes may not have any helium. So that relates back to the source rocks, and we can't really evaluate those. So how do we find it? Well, I think structure is important. I haven't seen a single strat trap yet. I know there's been disagreements about the Morrow, but if you really map the Morrow sands, you get little closures within the sand, and they typically tend to be the best gas wells. And that's where the helium is found. The Morrow is still a valley fill system, and externally it doesn't look like a structure. Salts and anhydrates are the best seals. Shales are great too, especially if you have a thick section. And I'll be talking about Los Angeles Arch here soon to show that. The reservoirs are sandstones or carbonates. I don't think we'll ever see this in unconventional, which is some ways fortunate, because I'm not sure how easy it would be to get out of those gases. But regardless, it's really a typical oil and gas play, except you're looking at very low percentages of product, and then you have to find enough of it to get it out cost effectively. This is by Weissman and Eccles. They have done a lot of work in putting together data sets. They have recently a publication on Utah and helium. It's very good. You should all read it. But they've done a lot of good work. The recent short course was very good. Well, that was with his partner McBride. But it gives us an idea. If you look at the country, there are basically very few areas that there's a lot of helium. So it tells us that whatever the source of the helium is, it's very restricted to these areas, and we have to look at those as potential sources. In a in the short course by Tyler Weissman, he mentioned Michigan stray sand up in Michigan. I don't think that's, I don't know why the helium's there. Michigan stray I chased for a while. It's a gas play. But generally, there are areas that haven't been analyzed, such as the Cincinnati Arch in central Tennessee. There's a lot of gas down there, but there's very few data points, so maybe there's potential there. But also note that as you go west of Utah, we basically don't see much of anything. There really is a lack of any helium accumulations. Lots of CO2 accumulations because of igneous activity, but not helium. These are the major producing areas in the US and Canada. After the first two, they're not really in any particular order. LaBarge produces 30% of our helium. It could produce actually 100% if the BLM allowed drilling into the national forest, but that's not likely. The Hugoton is near the end of its life. Then there's fields like in Diné by Kiwa and Pinta Dome. These are sort of the mid-size, and they draw you into an area. There's a number of fields that have been drilled for up there in the Four Corners area that have not turned out or they've watered out. Kansas has had its area that's just was awesome for a while. Then down in New Mexico, hogback, rattlesnake. They're nice fields. Oklahoma Keys Field, it's an oddity. It sits by itself. It's another Morrow sand. And then a really small type field that gets you excited if you fly high in numbers is the Harley Dome. And that's out near where I'm working. Major producing areas in the world, Qatar and Iran. Algiers' Hassan Armel is in serious decline. It's probably at the end of its life. So Algiers is scrambling because they make a lot of good money out of helium. Russia is the Amir plant. It's just a gas processing plant. So it's tied to two very large fields whose names I don't want to try to pronounce, but they have 1% helium or so. It's hard to get data out of Russia. In South Africa, they have a nice, interesting little field called Virginia. It's basically helium trapped in a reservoir. I think it's called white sand. Biogenic methane. It's coming up from the Witwatersrand below. Karoo is the host rock. And quite honestly, it's probably not repeatable anywhere, but it's still something to consider. It's very unique, but it certainly has set off a helium industry down there in South Africa. And then Poland, I didn't realize, has a lot of small fields. They're near the end of their life too. They're produced in two very tectonically active areas. The other nice thing, interesting thing, except for like in the Harley Dome, because there's no Paleozoic rocks underneath it, almost all the production is from Paleozoic rocks for helium. And then the other areas of interest is southern Saskatchewan, Australia, and the Tanzania we'll talk about briefly near the end. Well, this is Big Piney LaBarge. This is the big kahuna right now. Overthrust, nice big structure, the Moxa arches next to it. It's basically out of the Madison. That's another popular reservoir is the Madison limestone. Many of the fields in the US are producing helium from Madison. It seems the deeper you go, the more likely you'll find the reservoir as soon as you find something below a good seal. Essentially, there's very few wells in this field producing. All of the CO2 is used in secondary recovery. There are other fields on the southwest corner of that middle map that have good CO2, but the helium hasn't really been tested from what I can tell. The thrust is related to volcanic activity because of the CO2, but it's a supergiant for a CO2 field. North and South Pars, perfectly placed for the largest field in the world to provide the most helium in a politically unstable area. The field was discovered, I think, in the late 1980s. It's got 1,800 TCF of gas, and I think the calculation was around 1 TCF of helium. Simple geology, basically you have two salt basins, and then you have this large ridge between them. All the gas just migrated up there, and because it's only 0.04%, you can make it work. They're putting in what they call a train, which is really just a helium plant. They're putting in their fourth one. It should be online, but as I said, in Europe, they're saying that right now they're not producing any helium. I can't tell you why. Saudi Arabia and Qatar have had issues with each other. At one point, Qatar was shut down. Iran says they're not producing it, but they obviously have half the field, and they say they have the most helium reserves in the world. So take away what you want from that. This is in Algeria, another very simple field next to a couple of basins. The gas is all migrated out into this large structure. There's 3 sands. A, B, and C. The A sand being the best sand for production. Another, I think it's like 800 TCF of gas. Just an enormous field. But once again, it's very unique. It's, in some ways, if you can't find these things, you shouldn't be in the business. This is from Weissman and Eccles, and it basically is a nice display of showing where all of the helium data is in the middle of the U.S., and it tells you where to look. It basically the Four Corners area or Colorado Plateau area, southeast Colorado, western, Hugoton, Texas area, and then central Kansas as a primary areas to look, and then up in Wyoming. But essentially, you can see there's a lot of areas with lack of data, and we just don't know if what's there or not there. Also remember is that until recently, a lot of companies did not analyze for helium because it really wasn't something anybody thought about. Now this is the Hugoton field. As you can see, it's a huge field. It produces out of Permian sands, Permian carbonates, excuse me. And it's basically an up-dip trap related to the Anadarko Basin and the Amarillo-Wichita uplift. And essentially it's just produced for decades, but now it's running out of gas as well as helium. There are Morrow fields underneath it, and we will talk about those. Some have helium and some don't. But essentially this is the play that really set everything off after Dexter, Kansas, where helium was discovered. Okay, so some people like to turn the Four Corners play and just say Four Corners, but it's really, the play is about the Colorado Plateau. And the Colorado Plateau is like a raft on a sea of lava. Occasionally things break through, but essentially we see a number of deposits that, I noticed I didn't label a few, I forgot to do that. But essentially we see CO2 deposits in Utah. We see helium deposits in various areas that all represent venting from the subsurface. The problem with some of these fields that are being chased is that they are low volume, very high percentage. Some are well above the water table down in the Holbrook Basin. So essentially the Pinta field, like in number 5, or the Dina Kia Bai field, might be sort of like the Rangeley field up in northwest Colorado. Nothing else around it, big field, but it's the only thing in town. And then so far, we've not seen a lot of production come out. I believe it's a hogback field in northwest New Mexico. They put a lot of reserves of helium on it early on in the 40s or 50s, and then it went to water pretty quickly, and it was out of Devonian. Essentially, you have problems just like you do in oil and gas. And then a number of fields in Arizona are in younger sediments, simply because there's a lack of Paleozoics there. So essentially what we're looking for, I think in terms of a helium target, is where's the best seal that we would expect to hold it in the reservoir. And that could be as shallow as you want it to be or as deep as you want it to be. But several of the fields I put on the side, the Saltwash field in the upper left-hand corner, you will note that it's it's up in Grand County, Utah. It's a structural nose, Leadville again, Madison, Mississippian age, and Amoco had it, and the documentation's in their files with the state of Utah. They knew they had 1% helium. It was recommended they process it, and then Amoco did not do it. And that's typically, as I work for Mobil, we made decisions that ignored other products simply because it wasn't our focus. So there's nothing you can do about that. Harley Dome in the upper right. Lisbon Field has some helium and also CO2. It also has H2S, which is causes it to be limited. And then the Pinta, Navajo Springs East, and Navajo Springs Field on the bottom left. And you can see they're all structure related. Many of them have faults. Harley Dome, it's a nice structural nose. I'm working in the greater Cisco field area, and we're looking at helium as well as gas and oil, but Harley Dome has basically all nitrogen in the entrada. Shallower zones have some hydrocarbons, but very little helium compared to the entrada, which is above 7%. Now, one of the things, and this is just a quick overview, this is Harley Dome as well as the other areas I'm working. We use aeromagnetics a lot. Aeromagnetics helps you define the basement based on algorithms that, unless we drill them all and prove that the algorithms work, we have to assume they work. And what we did here is try to find out where the intrusions are, because there is some people who have the thought that helium is related to where intrusions are. And there's some validity to that. As you can see, the Harley Dome in the upper right-hand corner, there's a number of intrusions related to it, which could have provided the source for helium and the nitrogen. And then as we go to the southwest in Cisco Springs area, our helium drops down. The helium in the Cisco Springs area has not been tested below the Dakota, so we don't know what the intrada looks like, and we'll do that later this year with some drilling. Then over in the Cisco Dome, which is a good-sized field, it's made about 16 BCF of gas, a couple million barrels of oil. We've analyzed all the wells because we're now the owner of the field, and there's no helium in the gas. And as you can see, there's really no intrusions. So this could be a good tool to use. And then the basement faulting defined by aeromagnetics. Once again, that's based on tightness of gradient and algorithms. So that's, really up to the individual to determine if they believe that. And then this is just the migration model that was developed for it. I forget where it came from, but it's a good model. It's useful in any model, and it's probably very reasonable. Then just jumping into Kansas, in the Greenwood field is part of the Yucatan. You can see the amount of drilling. That volume of gas, you can strip out a lot of things, not only helium if it's there. And then Otis Albert, which is basically is first an accumulation in the Cambrian sand, excuse me. And then eventually they developed everything above because it was also full of helium. But it's up against a Precambrian ridge that's northwest southeast. This is central Kansas uplift. And so the sand just developed in a low. Perfect trap, fields at the end of its life. There's a number of fields up here like this. As a matter of fact, it's very interesting how basically the area is mainly all oil except for where you find helium because there's natural gas. Ryerson, central Kansas. This was done by David Newell and others. Nice little field. American Warrior turned this into a good producing field for helium, but it took a commitment by an operator to spend the money. As I will discuss, the biggest cost in developing a field yourself for helium is the cost of the processing plant. And in some areas, like in Southeast Colorado, there's options such as selling the gas to the processing plant, and they'll pay you for the helium. Okay, Los Animas Arch. This is an area that is really befuddled a lot of people, not just for finding helium, but for finding oil and gas. Essentially, this is Southeast Colorado. You can see the Hugoton to the southeast, the Keys Dome, which is a major helium-producing area. And then the upper circle in Cheyenne and Kiowa, that's been a major helium-producing area, as well as oil from the Morrow, and also oil and gas from the Spurgeon and some of the shallower Pennsylvania units. And then the general Denver Basin. The green splotches everywhere is the production. You can see how the helium content goes down as you go deeper into the basin, up into Lincoln County. And then down in Los Animas Arch is the Episcopal uplift where Model Dome is. We'll talk about that briefly. But that's really in a different tectonic environment and probably not in the Raton or the Denver Basin. So a friend of mine said that he thought that the helium was being generated with black shales in the Morrow. Well, there isn't many black shales in the Morrow. There is a lot in the overlying major seal, as marked on here, because that's the Marmaton, Cherokee, and Atoka. There's probably 13 highly organic radioactive shales in the Atoka alone. There's 3 or 4 in the Cherokee, a couple in the Marmaton, and on top of that, the Atoka's carbonates are very dense, have no real porosity permeability, and I can vouch for that because I tried to frack them a couple of times to get the oil out of the Atokan, and we screened out pretty rapidly. But the Morrow is a very porous environment. The sands act as wonderful reservoirs, and below it, in the section below it, which is basically Mississippi and older, is basically wide open. This has been shown to be proved in a number of fields because there's fracture, they're faulted. Well, you see a lot of these fracturing faultings die above the Morrow, so therefore the Morrow sands are probably the best trap. But why particular certain areas for Morrow sands? Because there's several Morrow sands that have gas in them, but they're barren of helium. Well, let's take a look at that. I'm using the basement map from the USGS, recently published for Colorado, trying to get data for Kansas, and that's why it stops where all of the Los Animas Arch area stuff. But notice that major fault running northwest, southeast. And there's also one running down near the Keys Dome. And so the data sort of lines up with that. Early early thoughts were that oil was coming out of the Anadarko Basin that was filling up in the Los Angeles reservoirs. And that may be true on the east side of it, but on the west side of it, that's highly unlikely because it's hard, in my mind, to go over a topographic height and go down. But notice that all the data that's down in the Hugoton is much lower than around in the areas where the Morrow production is from the Keys Dome and from Cheyenne and Kiowa County. And there's some things going on in the basement. Just remember, just because you have a lot of faulting and breakup in the basement that you can map with different rock units doesn't mean you have a play. This is Morrow wells only. Once again, you see that most of the Keys Dome, look at the Morrow wells around it. There's several fields, and the data is generally very low. You go up to the fault area, that's northwest, southeast, and you can see a lot of good numbers falling near that fault area. Now, there's some further down in Kiowa County, but there may be just a basement fault we're not seeing yet. But then as you go further south into southern Kiowa, down into Bent and Prowers, there's Morrow fields, but they just don't have much helium. And the same is true as for west into Lincoln County. And then, oh, this is, I took Bowman's, it might be hard to see and I apologize, but the little squiggly lines are Bowman's and Weimer's sand map that they did for the Morrow. And you can see that a number of the oil fields fall near this fault system too. And maybe the oil was generated by upgrading, migrating low temperature hydrothermal fluids from the basement and generated in the shales. Who knows? It's just a thought. But essentially, the good Morrow areas with helium also correlate with the Morrow channel system. Then this is Permian wells only, and you can see that there's really nothing anywhere in Colorado that gives you good Permian data, which suggests that maybe a token through Marmonton is acting as an effective seal. Now this is the Arrowhead field, just showing this to show you that there's little structures within inside the field, and that's where we're seeing the gas and the helium. Helium just likes to be at the top of the game, probably because it's small and just wants to feel important. But regardless, it just gives you an idea that internally there is structure in these fields, and that's where you look for in my mind, the helium. The Model Dome, this has become a hot discussion in LinkedIn and some other places. For people who don't know, this is what Blue Star is chasing. This area has a nice little feature. There's hardly any drilling in this county. This area has gone through 3 or 4 phases. Personally, I think this is like a one-off, like a Harley Dome, but there's still a lot of work to be done, but I just don't see where this field to be any bigger than what it is now, just my personal opinion. Tanzania is another, supposedly world-class and that sort of thing. Well, the problem is that in all of these tectonic areas, there's a lot of helium on the mid-Atlantic ridge system coming out, but that doesn't mean there's reservoir and places and ability to capture it. The south of the orange area is where they're looking, but I will tell you is the British did look for this helium in the 50s because the British needed it, because just for the reasons we need now for healthcare and all sorts of other welding and that thing. And there's going to be some drilling soon, but I think this is a high-risk play, and putting a number of what did they put on, a TCF of helium or something outrageous is a little out there, but it's entirely their prerogative. So how do we evaluate helium? And I say good luck because it really is still in the early stages. We don't have any Pathfinder tools on the helium itself. We don't get data because helium is not taxed separately as far as I know. Typically, once you take the gas from the wellhead and put it into a processing plant, well, they've already paid taxes on it. Now, that may be different for some operators. Collecting data on what wells that produce helium requires a lot of investigation. As you can imagine, if it wasn't for the BLM and the U.S. Bureau of Mines, we wouldn't have the data we have, because they call up people and they tend to answer their questions because they're with the federal government. There's 3 types of plays. The ones we're dealing with in the U.S. are probably only the medium and the low grade. And this is where oil scouts would be good, because I remember early on in the start of my career is that oil scouts seemed to know what's going on. Even when I was on a rig, I didn't know what was going on, and they knew more than I did. What tools do I need to make a helium play? Structure is critical. Reservoir, sandstone, limestone, or dolomite. Near basement tectonic activity or large-scale basin expulsion. So basically, you're where everything backs up at the end of the migration path. Typically, Paleozoic are older rocks, but this is not necessarily true of the Colorado Plateau. But younger rocks in other areas are very high risk. The greater the volume of the helium, the lower the greater the volume of the helium, the more reserves you need in terms of gas in order to make it work. Host gas can be any of these three. Exploration methods, existing databases, testing existing gas wells for helium, petroleum system analysis, looking for areas where subplays for helium is possible, areas of thermal activity. I haven't talked about surface geochem as much, but it's useful and can help to find helium plays. But it's like any other surface geochem, is you have to eventually drill it, ruin a good prospect with drilling. And then seismic to find the structure and make sure you have a trap. The trap is critical to helium more so than I think oil and gas in some respects. Developing process method. This is the killer for the independents. Is basically a cost about $1.5 million to $3 million for a pressure swing absorption unit. Cryogenic units start around 10 million. And this is where you need to make sure about your reserves, your ability to deliver the gas, and that the helium. Another problem with helium percentages, they can change with production over time, just like a lot of things can change with oil and gas reservoirs over time. So that's the biggest cost. If you have nitrogen, you can vent to atmosphere. If you got a little methane with it, then you can use that for power. But nitrogen causes higher electrical costs. And then getting rid of the methane, where it's a methane dominant, is pretty important because of today's political climate, as well as CO2. In summary, helium is a critical element needed for modern society. Helium is related to uranium and thorium decay from granitic rocks and within Paleozoic carbonaceous shales. Excuse me. The majority of helium is produced by U.S., Qatar, Algiers, and Russia. China's now got a processing plant they put in. They got smart. They might as well run all their gas through their processing plant because they can make that economically work, because they don't seem to have any helium deposits per se. Central part of the Mid-Continent, Central and Southern Rockies is the areas of U.S. production and focus. Southern Canada, Saskatchewan's becoming an area of focus, northern Montana, but it's in early stages. Finding these reserves is difficult. Helium is an opportunity for many independents to provide additional cash, but you have to be, like any oil and gas play, is be willing to go to the end game, which is to build that plant. And recovering the gas is expensive. However, like I just said, helium provides a unique opportunity. And thank you.
Thanks, Steve. That was awesome. That was really, really nice. Good summary. There is a question. Anything in the Appalachian Basin, Rome Trough?
Well, based on the data we have right now, no, but I have actually wondered about that. But it comes down to, you have gas wells in the Rome Trough. If you don't, there's no way to know. And then how do you convince somebody to drill a test in the Rome Trough if you don't know if there's helium there? If you can convince somebody, let me know. I got a bridge they can buy too.
There's a question from somebody, or kind of a comment, I guess. What are your thoughts on Alton Brown thinks that some of the helium, the Hugoton Panhandle fields, comes out of the Dalhart and Paladuro basins, in addition to the Anadarko?
I think that's that's probably likely and very true. Tyler Weissman and I had talked. He sent me some information. I just don't think, since you can't type where helium comes from, you have no idea. And so it comes down to is where you believe the migration comes from. I think that it's up in the air where the Texas Panhandle, Hugoton. I think some of the helium there came from the rocks right below as well. So I think it's just a combination of things.
Yeah. There's another comment regarding the helium in South Africa, that the South African helium reserves are in the Witwatersrand. The Permian is only a potential play right now.
Okay, I may have gotten that wrong.
But didn't know. What is the geologic story with helium in north central Montana? Is this an active field?
No, there's helium up at the the Bowden Dome, There's up there is Rudyard field has been chased for helium, but essentially there's really very little helium in Montana, but there's also very little drilling across from the Saskatchewan plays, which are in the Cambrian deadwood sand. So it's sort of like people got some numbers in Saskatchewan and they're now migrating down into there, chasing the sand, which is how an oil and gas play usually works.
Mm-hmm. How is helium trapped, given the smaller molecule size?
Well, it seems to be there are actually a number of minerals that can trap helium and hold it for longer, but it just seems to be the proponents of a lot of rock volume sitting there. I would also think that the helium has to move past things, so it's like all plumbing. It gets if you got big stuff in there, it can plug it up. But we have helium deposits, so it's obviously not migrating out.
Ron Parker's curious about the age of the helium-4 as Precambrian. Once uranium-235 or uranium-238 have reached secular equilibrium, there is a lot of alpha decay steps that are quick. Shouldn't these yield newer helium-4?
Your guess is as good as mine. Everything I read is, it takes so long to generate helium. And I don't think anybody really knows. That's one of the real problems. It's all conjecture.
Yeah, if you can't type the source, that's, yeah, makes it
Yeah,
pretty.
it's not like I can point to, the Bakken Shale and say that's where it came from, because
Yeah.
we don't know what's in the basement. I'm betting in some areas there's a lot of uranium, an incredibly large amounts of uranium sitting there generating helium, like maybe in southeast Colorado, but we just don't know about it because no one's drilled it.
Mm-hmm. Why is helium-3 so much more valuable than helium-4, and what percentage of most deposits are helium-3?
Helium-3 is about 0.001% or 00. It's almost infinitesimally small of all helium that we find. And helium-3 just has better characteristics for doing fusion than helium-4. In other words, I think there's a neutron missing, and I'd have to go back and look. I can tell you is that when I started researching my book, I was overwhelmed at all that isn't known and all that is out there in terms of helium. But I right now, but helium-3 is best for fusion reactions.
In the Colorado Plateau, is there a relationship between helium and uranium and vanadium deposits? Vanadium deposits?
I don't know, but I do know that there's a lot of uranium and vanadium deposits in Grand County, Utah.
Hmm.
And that's probably all I can say.
Is there any helium from granite washes or anything?
Well, if they got uranium and thorium in it, I guess they would.
Are there any fractured helium reserves? I think you're getting a lot of people are turning the wheels on prospects here.
Yeah, I think there's fracturing related with all helium prospects, hopefully only in the reservoir, not in the seal. So, but I think that's one of the things interesting about Southeast Colorado is that the helium's trapping in the Morrow sands, but then you have this dense, and there is no salts in the middle to upper Pennsylvanian, but there's a lot of dense limes and shales. So I think that's the seal. But I think everything below is fractured. So.
You say the large methane and CO2 fields are better targets for economic deposits rather than nitrogen-rich ones. What is the?
No, I think they're about even. I think they all three have different problems. For example, if you have a methane deposit, but you can get rid of your natural gas, that's great. That's a good deposit. But there are a lot of natural gas deposits with helium that are stuck in the middle of nowhere, and you can't vent the gas anymore. Not that you really want to, but putting in a pipeline is, well, I know in Kansas is 150,000 a mile. So if you're 20 miles from somewhere, you better have $3 million of money coming out of that helium deposit. Nitrogen is fine because you can vent it to the atmosphere, but then you have, like Harley Dome, is they're always on propane, so that's a real high cost for them. And if they were large in size, it might even be a bigger problem because you need the power to run the plants. And then CO2, same thing as methane. If you're in an area like in Wyoming, where they're using the CO2 for oil recovery, that's great. But if you have no place to send the CO2 in your middle of nowhere, it doesn't matter if you have 8% helium, you're going to have a problem getting rid of that CO2. Whether you put it back into the ground, it doesn't matter. It's a political nightmare. And if you're especially on federal ground, which you'd like to be in the western U.S.
Yeah. Hold on, I'm just reading through the questions here. Denver Basin fluid expulsion and the helium in the Arickaree Creek field. Could the discontinuous Mississippian aquifers play a part in the migration to areas on the Cambridge Arch and northern Las Animas Arch, in your opinion?
Yes.
Yes. What is the estimated life of LaBarge deposit at current depletion rates with existing wells? And how many BCF of helium are there?
I can't really answer all of that. To me, it's technically, I've been told by engineers that if I put one well in a field, it could technically drain a field as long as you can keep producing it for the rest of its life. So they could drain a very large area from there. I don't know the reserves for helium offhand. And then the CO2 is the production from the field is actually dependent upon if they keep using it for secondary or tertiary methods.
Yeah, over at Salt Creek.
Yeah.
All right, Steve, it's 1 o'clock, and that's kind of it for questions. We really appreciate your time and your presentation, and thank you.